Okay, so hopefully you all watched the video I asked you to watch, because if not, like, the first half of class is going to be very confusing. So here's a little box. Type of reaction. No, a little box. So a large portion of your exam is going to be determining what type of reaction you're doing and then providing the product, right? Right now, you only know substitution reactions. So we need to be able to determine if you're doing an Sn1 or an Sn2 reaction. The first thing you want to do you want to look at the halide, specifically the type of halide. So what kind of halide is this bromide? Is it primary, secondary, or tertiary? It is secondary. Great. So this is the first thing that you need to kind of bash into your brain, right? For Sn2 reactions, only primary and secondary halides can do Sn2 reactions. For Sn1 reactions, only secondary or tertiary halides can do Sn1 reactions. So the fact that this halide is secondary, sadly, not super helpful right now. The next thing you want to do is you want to look at your nucleophile. Is my nucleophile here, is it charged or uncharged? The super easy way to make this decision quickly is to ask yourself, does it have a metal? If it has a metal, it's charged, right? So NaOH has a metal, so it is charged, right? Remember, you can break it in half. The metal side is positive, the thing bonded to the metal, in this case, the oxygen, is negative. So even though there's not charges clearly shown, the fact that there is a metal lets you know that there's one thing that is plus and one thing that is minus. And the nucleophile is going to be the minus thing. So charged, that supports or promotes Sn2 reactions. Now we look at the solvent. What kind of solvent is this? Is it a polar protic solvent or is it a polar aprotic solvent? These are the things that we went over on Wednesday. You just have to know these 5 or 6 things. This one's aprotic. DMF is polar aprotic. Right? DMF looks like this. There's no OH and there's no NH that can do a hydrogen bond. Polar aprotic solvents, those promote Sn2 reactions. So we have a halide that can do an Sn2 reaction. We have a nucleophile that is charged. This is do an Sn2 reaction. We have a polar aprotic solvent that says do an Sn2 reaction, but you were doing an Sn2 reaction. So our type of reaction here is going to be Sn2. And now what is our product going to be? We're going to make an alcohol. We're going to have the OH replace the Br and make an alcohol. Again, we have a secondary halide. Not super useful. right? Still, it could be Sn1 or Sn2. What type of nucleophile is water? Charged or uncharged? Uncharged. If it has no metal, it is uncharged. Doing the exact same thing I did in the early class where I don't leave myself in a space. So this is uncharged. And it just so happens that this also is our solvent. Is this solvent polar aprotic or polar protic? Does water have an OH in it? That means it's got hydrogens for hydrogen bonding. So this is a polar protic solvent, right? So it's uncharged. Uncharged favors Sn1. Polar protic solvents favor Sn1. So together, we know we have a halide that can do Sn1 reactions, an uncharged nucleophile, a polar protic solvent. All those things together are saying, hey man, do an Sn1 reaction. What is my product going to be? Another alcohol, the exact same thing. And you may be thinking, why did we go through all of this? It didn't matter what reaction was what, you still got the same product, right? Where it really starts to matter is if you have stereochemistry, right? So let's say I do the exact same reactions, but I introduce stereochemistry on my leaving group, on my halide. Right? Exact same reactions. So we know the first one is going to be an Sn2 reaction. What is one of the big features of an Sn2 reaction when there's stereochemistry? You invert your stereochemistry, right? Your nucleophile has to attack from behind. So that means you have to identify what type of reaction it is so that your product has the right stereochemistry, right? So if your leaving group was forward, your nucleophile is going to be back, right? Now, in an Sn1 reaction, you go through a carbocation, right? So your mechanism, you make a carbocation. Carbocations are flat, right? So what that means is you have a 50% chance of your nucleophile coming from the top and a 50% chance of your nucleophile coming from the bottom. So what that ends up being is you end up making a racemic mixture. You get a one-to-one mixture of wedge and dash. So what I usually just have you guys do is I don't have you worry about the stereochemistry. I just have you draw it as if it had no stereochemistry because it's a one-to-one mixture. So if you get your type of reaction wrong, then you're going to mess up your stereochemistry. Right? If you thought the first one was an Sn1 reaction, you'd be like, oh, I don't have any stereochemistry. Right? Now, like in a normal semester where you like have to write all this stuff out, right? I would like give you partial credit. But now we're under the tyranny of Moodle and multiple choice questions. So, right, I could very easily for this first one give you three options: alcohol that is a wedge, alcohol that's a dash, and alcohol with no stereochemistry. Right? So you have to know, okay, what reaction is it? Okay, it's an Sn2 reaction. So then I'm going to replace my bromine or my leaving group with an OH, and now I have to know what stereochemistry that I have. right? So I could give you all three answers are 2-butanol, but you have to know if it's R or S or no stereochemistry, right? Knowing what reaction you're picking helps you do that. So when we're doing these, right, the first place I always have us look is I always have us look at the halide, right? What type of halide it is. Because the halide has veto power, right? If the halide can't do a type of reaction, it doesn't matter what everything else is, we're not doing that type of reaction. So if I have a primary halide and um, I try to do an Sn1 reaction, primary halides can't do Sn1 reactions, so that reaction is not going to happen, right? If I have a tertiary halide and I try to do an Sn2 reaction, I'm not going to do an Sn2 reaction. I'm going to do something else, right? So your halide always has veto power. So when you're trying to figure out what your reaction is, right, you can just start by looking at your halide. What type of halide is that? What type of halide is the iodide? Primary. Primary halides only do Sn2 reactions. Congratulations, we're doing an Sn2 reaction. Right, now we can look and say like, oh, hey, cool, my nucleophile has a metal on it, so it's charged. My solvent is polar aprotic. Those things also support me doing an Sn2 reaction. But your halide gets to say, hey, I do Sn2 reactions. Full stop. I don't do Sn1 reactions. Right? So then you just have to go like, okay, I know it's an Sn2 reaction. I'm going to make my product. What type of halide is this chlorine? It is tertiary. What kind of tertiary halides? Do they do um, Sn1 or Sn2 reactions? Sn1. Had two people pop up on Zoom. They're too excited over there in like their homes. This is great, right? So I'm going to replace the chlorine via an Sn1 reaction, and I'm going to put my amine there. As far so good. So what's my first one? Sn1 or Sn2? It is Sn2. But your halide here is secondary. Your nucleophile is charged, right, because it has a metal, right? This one you're going to have sodium plus, and the carbon bonded to the sodium is going to have the minus. So that carbon is going to be the nucleophile. And then this is polar aprotic. So we're going to make our product. And we're going to invert our stereochemistry. We're going to go from wedge to dash. And just to remind everyone, Cn, that is C triple bond N. So if you see it written Cn or C triple bond N, it's the same thing. What kind of reaction is the bottom one? It is Sn1. Right? Secondary halide, and then an uncharged nucleophile that also is a polar protic solvent. So if you remember, a lot of Sn1 reactions are solvolysis reactions, where the solvent also serves as the nucleophile. So here, ethanol is what we dissolve our bromide in, and it also is what ends up displacing that bromide, doing the Sn1 reaction. My product is that. And you're probably like, I had this all down. What happened? Right? So if you remember, mechanism goes through a carbocation. That's a secondary carbocation. Whenever you have a secondary carbocation, you have to look at it and say, hey, can I do a rearrangement? Can I move a hydrogen? Can I move a methyl and make a more stable carbocation? In this case, we're able to move a hydrogen. And make now a tertiary carbocation. So I go from secondary here, secondary carbocation, to tertiary. Then I add my ethanol and I get my product. So whenever you add an alcohol, right, you always end up making an ether for your product because you're never going to break the carbon-oxygen bond. So what happens in this, I'm going to go, right, I get my carbocation that I'm going to add to after the rearrangement. And I add my ethanol. And I end up with an oxygen with 3 bonds, right? And I want to get rid of one of those 3 bonds to end up with an oxygen that has 2 bonds and is no longer positive, is neutral. It is way, 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 way easier to get rid of the oxygen-hydrogen bond than it is to break either of the oxygen-carbon bonds that you have. So you're always going to just lose a hydrogen and make the product than as opposed to breaking the carbon-oxygen bond. So whenever you're adding an alcohol, just think that you're going to take your oxygen and add it and all the hydrogens attached to it to your carbocation that you make, as opposed to losing those carbons and just adding OH. So it's always oxygen plus the carbons. Another thing to consider is when you have double bonds or aromatic rings involved in your molecule. So this halide here is primary, but it's also allylic. So a primary allylic carbocation, primary allylic halide can do Sn1 reactions because the carbocation that you generate has a similar stability to a secondary carbocation. So if this halide leaves, I get an allylic carbocation that is resonance stabilized, that I'm able to move electrons over and move that charge. So instead of that carbon, the carbon that had the halide, we'll make it blue, right? Instead of that carbon being 100% positive all the time, right? It's able to shift that positive charge onto another carbon, right? So that positive charge bounces back and forth. And so it's spread out across two carbons. So this is similar to a secondary cation, right? So we're able to make that carbocation and then add water to it. So this can be an Sn1 reaction because that halide, when it leaves, it makes something that is roughly as stable as a secondary carbocation. And we're able to make our alcohol. Say when you have a halide that is benzylic, that is on the benzylic carbon, so this carbon right here, that carbon is the benzylic carbon. Okay, this halide is primary but benzylic. So when it makes a carbocation, that carbocation is more stable than if it were just a primary halide without being beside an aromatic ring. So this can do an Sn1 reaction. All right, you're adding an alcohol, so you always make an ether. So when you have the allylic cation, you're spreading that cation on over two carbons, right? It's spreading between this green one and this blue one. Sorry, green one and blue one. There we go. Right, so those two carbons are sharing the positive charge. When you have an aromatic ring, when you have a benzylic carbocation, so this iodide, right, when it leaves, right, we make that carbocation. We make this benzylic carbocation. And it has a bunch of resonance structures. It's able to move that carbocation around to a bunch of different carbons. So I'm able to move that carbocation to that carbon. Then I can move it again to this carbon. I can move it again to that carbon. So instead of that one primary carbon being positive all the time, that positive charge gets spread out across three other carbons. So there are 4 carbons total that are sharing that positive charge. So they're not all 100% positive, they're all a little bit positive. It helps make that carbocation more stable. So we're able to make that primary carbocation because that primary carbocation is stabilized via resonance. So if someone asked in the early class, like, I didn't think we could break an aromatic ring, right? If we have an aromatic ring, it's supposed to be really stable. We're not supposed to like mess with it. And what we do is our human brains are very dumb. And we have a really hard time thinking about how molecules actually kind of behave. So when we draw resonance structures, we draw the extremes, right? We draw this structure. We draw this, this, and this. So we can think about what the molecule is doing. In actuality, the molecule is never any one of these 4 structures. It's some like weird average of the 4, right? So this carbon is never 100% positive. This one's never 100% positive. What ends up happening is maybe this carbon is 0.4 of a positive charge, and this one's 0.2, 0.2, and 0.2. And so you get a whole positive charge, but you've spread it out across multiple carbons. So there are just slight differences in how positive each carbon is. But we have a hard time thinking about like, oh yeah, this is 0.2 plus. Like, no, our heads don't work that way, right? So we draw just the extremes. And that can show like, hey, this charge can move around, so it must be more stable than just being stuck on one thing. But then we have to take the step and go like, the molecule never does all of this, right? The molecule is just like some weird average of these, but this carbon is positive enough that the nucleophile will add there. So far, so good. I know resonance hurts people's heads, right? Because you're trying to think of things that like we're using examples to explain things that don't really happen, right? We're just trying to get our little heads around how the molecules act. And the way the molecules act isn't quite this. But this is the best way we've come up to do it. So, and then this came up, someone was asking this. So if you have a structure, or you have, let's say, a double bond, a CH2, and then an oxygen, right? Can this oxygen and its lone pairs interact with this double bond? And the answer is no, because they're not close enough, right? You have to have resonance, you need to have an atom that has a lone pair or a positive charge or a negative charge, and it has to be right beside a double bond or another atom that has orbitals it can interact with. So right here, this carbon here has 2 hydrogens. All of its orbitals are full, right? So it has no way to like take electrons from anything else. It's just cool. Now, if these were right beside each other, now the lone pairs on this oxygen can interact with the electrons of the double bond. These electrons can push down and push electrons over, right? So the lone pair on the oxygen is able to push the electrons from the carbon-carbon pi bond into the p orbital. So now you have you have 2 electrons in the p orbital that was being used to make the double bond. And just like before, again, the molecule's never 100% this or 100% that, right? Molecules spend most of their time right? Or behave most like the resonance structure that doesn't have any charges, right? Because having charges in your molecule is high energy. So maybe the molecule acts 70% like this and 30% like this, right? These aren't real numbers. Don't like take me to like chemistry police and be like, yo, he gave us these numbers. Okay? But the point is, it acts most like this, but it has character like this where it has a carbon that is negative, right? So that can explain how this molecule behaves, how it reacts, because oh, I can use it as a nucleophile. It can add to things. Well, how can I explain that? Well, it has some character where this carbon is negative. So that makes sense. Like, oh, that carbon is negative sometimes. I can use it as a nucleophile. So we use resonance structures to kind of explain reactivity sometimes when it might not be clear just looking at one resonance structure how that molecule behaves that way. And then one more thing that got asked in the early class is, okay, so from when we drew that product before, right? There are two resonances of an aromatic ring you can draw, right, where the electrons just kind of move around. Right, you can have it this way, or you can have it this way. And the only difference is the position of the double bond. Don't care. They're the exact same thing, right? In reality, the double bonds in benzene or in aromatic rings move really fast and they stop kind of being distinct double bonds. But again, we have smooth brains. So we have to just kind of show like, hey, they can be here or here, but they're the same thing. So don't like stress if I like draw an aromatic ring with one resonance structure and then I draw the next aromatic ring with the other, it's the same. So we feeling good? More or less. So we've got all our substitution stuff in our heads, hopefully. Hopefully we can look at a reaction and go, hey, that's Sn1 or Sn2, and then get the product. The next thing that I want to do is I want to start doing eliminations. And we're going to get just a little bit into this. And then we'll finish up eliminations next week, and that'll be on your exam. That should probably be like the last thing we cover is like this set of slides will be the last thing that's on the exam for the exam on Friday. So elimination reactions, right? There are two types. Two types. There's E2 and E1. Thankfully, when we got together and did this as like chemists, right, before my time, we decided that E2 reactions behave very much like Sn2 reactions. And E1 reactions are analogous to Sn1 reactions. So a lot of the same things that you learned for Sn1 and Sn2, they carry over, right? Your generic elimination reaction, right, is you have your leaving group, you have a base, and you make a double bond. You spit out your leaving group as a negatively charged thing, and then you make the conjugate acid of your base. So that's kind of your generic reaction. Now we're going to start with E2. And just like Sn2, the name is telling us something about the reaction and the mechanism, right? So the E is for elimination, duh. And then the 2 is because you have a bimolecular transition state, right? In the transition state, you have both the alkyl halide, or the thing that has your leaving group, and the base are both present in that rate law, just like the Sn2 reaction. Just like the Sn2 reaction, your base in this case is charged. Right? It's a strong base. And it grabs your hydrogen. Electrons come down and push off your halide. And give you your product. So this is a single step reaction, right? The base is pulling your hydrogen off, and your leaving group is leaving, and you're making your double bond all on a single step. Your halide and your hydrogen must be anti-periplanar. That is a whole lot of syllables for on opposite sides. Right? So your hydrogen and the halide that's leaving have to be on opposite sides of the molecule. So in an Sn2 reaction, right, your nucleophile had to like sneak up on your leaving group and push it off the molecule, right? So it had to come from behind and push it off, right? Here, you need to have the electrons in your carbon hydrogen bond. They need to be behind the electrons in your carbon leaving group bond, right? So that they can come in from behind and push the leaving group off the molecule. So you always want to have it that your hydrogen is arranged so it is behind the leaving group, so it's able to use its electrons to push it off. So where this can come in or come in play for reactions sometimes, and we'll do more examples later, is let's say we have this, use a generic base in an E2 reaction, right? So when we do these reactions, just like we did for making alkenes at the end of the alkyne section, where we have our alpha, beta 1, beta 2, and we're going to follow Zaitsev's rule. We want to make the most substituted double bond that we can. Well, it just so works out that beta 2 has the least number of hydrogens, and the hydrogen is on the opposite side of the ring from the iodide. So great, I can do that elimination. My base can come in, grab this hydrogen, push off my leaving group, and I'll make this double bond. I'll make the most substituted double bond. So now here I have the diastereomer, right? I've changed the stereochemistry on the methyl group. Where does that put the hydrogen? That puts the hydrogen on the same side as the iodide. Right? The base wants to follow Zaitsev's rule, wants to make the most substituted double bond. But because this is an E2 reaction, what's more important is that can only take a hydrogen if it's on the opposite side from the leaving group. So here, my hydrogen and my iodide are on the same side. So I can't remove the hydrogen from beta 2 because they're not on opposite sides. So what ends up happening is I remove a hydrogen from beta 1, right? It has two hydrogens. One's a wedge, one's a dash. It's going to take the hydrogen that's on the opposite side from the iodide, and it's going to make the least substituted double bond. And give us our product. So this being anti-periplanar, having to be on opposite sides, that can overrule Zaitsev's rule that we had learned before, because the way the mechanism works is they have to be on opposite sides. And if they're not, you can't do the reaction. So even though you know the rule that you have to apply, you have to also make sure, does the reaction work with the way the halide and the iodide are, or the halide and the hydrogen are arranged? Someone had asked in the early class, well, what if the year is just groups like beside one of the beta carbons, right? So alpha, beta 1, beta 2. And there might be some way that you can differentiate beta 1 and beta 2, but if you have something like this, you're just going to end up mostly getting a mixture, right? Because they're both beta 1 has two hydrogens, beta 2 has two hydrogens. So there's no difference in Zaitsev's rule. So you're probably just going to get a mixture of these two compounds. Right? So the main thing that's going to differentiate stuff is like how many hydrogens are on the carbon. Having groups beside it is not going to impact, or beside the beta carbon is not really going to impact which one reacts. Just as a reminder, right, your double bond, in E2 reactions specifically, but you should always expect your double bond to end up between an alpha and a beta carbon. Right? If you got your double bond in some crazy place, you're wrong. Right? So just kind of what we did before, right? The carbon that has the halide, right, is alpha. And then the beta carbons are your carbons that are bonded to your alpha. Right? So, just like we had done with the alkene synthesis, right? If you're able to label your alphas and your betas, you know what your options are for where your double bond's going to be. Right? So if you kind of start each problem doing that, you can then go like, okay, I know where my double bond has to end up. So, I think this is a reasonable place to stop. We'll finish up the E2 stuff and the E1 stuff, and then we'll spend a lot of time differentiating Sn1, Sn2, E1, and E2. So basically what we did at the start of class today, but we're going to throw in two more reactions. And we'll work through how you differentiate those. So, yeah. And then, like I said, I think this will be the last set of slides that'll be on the exam. We should get through the whole set of slides by the end of the day on Wednesday.